Hello, everyone. Paul here. Today to talk about light. Next time, we'll talk about telescopes and the sun, but for today, we want to talk about light. So, light is really kind of fascinating stuff. It is at the same time both a wave and a particle. So, it is something that moves through something else, disturbing it like a wave does. Don't ask me what light disturbs as it moves. That takes you somewhere you really don't want to go. Okay, but it's also a particle. It's also a discrete thing that can move around and hit things and stuff like that. So we're going to examine it in both ways because you have to in order to really understand it. But we're going to begin with light as a wave. This is the way Johannes Kepler understood it. This is the way Isaac Newton understood it. And it's really the first way that light was understood. So if it's a wave, it has a wavelength. And what we want to keep in mind is that what we call visible light is really a very small part of a much larger electromagnetic spectrum that runs from gamma rays down here. Let me make it so y'all can see me pointing a little bit better. There we go. That runs from gamma rays down here all the way up to AM radio waves up here. Wavelengths down here are very, very short. And these rays are very, very dangerous. Electromagnetic energy up here has very, very long wavelengths, 100 meters or so, and you're being exposed to these all the time, okay? And so, yeah, not dangerous at all. They also travel a very long way. You can pick up AM radio from Cuba here in the Tampa Bay area. Now, light, what we call light, is this bit right in here, right, that our eye has evolved to be able to see. And within that area of visible light, different wavelengths correspond with different colors, right? Red being longer wavelengths down here, and then violet being shorter wavelengths over here. And hold on, I need to get a drink of water. And so violet being shorter wavelengths down here. When you see color, by the way, this is what you're seeing. When light hits an object, some wavelengths are reflected and some are absorbed. The ones that are reflected are the ones that you see. The ones that are absorbed are the ones that you don't see. That's why objects are different colors. Now, because light is a wave, light refracts, right? It bends as it goes from one medium to another. So I have a prism here, which is just a triangle made out of glass, and white light comes in. As it goes from the air to the glass, it bends a little bit. As it goes from the glass back to the air, it bends a little bit. It bends according to something called Snell's law, if you're really interested and want to look it up. But notice that it goes in as white light and comes out a rainbow. Okay, that's because these different wavelengths of light refract at different angles. Shorter wavelengths of light refract more than longer wavelengths of light, right? So the violets and the blues down here are refracting more than the reds up here. So by the time it comes out, all of these wavelengths are broken out from each other, right? So it goes in white light, comes out a rainbow, okay? And by the way, this is how rainbows form, by the way. They just do it in droplets of water. Rainbows also require a little bit of reflection to work, and so light comes into this water droplet. It refracts as it goes from the air to the water. Then it reflects off of the back of the water droplet, comes out, and as it comes out, it refracts again, right? Further separating out the different wavelengths, and by the time you're done, you have that, right? Really nice, really pretty rainbow. Here's the thing, though, if I come back here for a second, the sun is back here behind the viewer, right? So whenever you see a rainbow, the sun will be at your back. It has to be. That's the way the optics of this work out. You will never see a sunset over here, behind a rainbow like that, right? I just went and Googled rainbow sunset, and sure enough, got photoshopped pictures. This is not possible, okay? This will not happen. It's really pretty, but it's not actually optically possible, okay? So if we run white light through a prism, we get a rainbow on the other side. Okay, when we do that, this is called a continuous spectrum, right? You've got all of the wavelengths of light present, right? All that I'm doing here is running white light through a prism, only now the prism is on its side, not up and down, and there you have it. Okay, now, that's fun, and that's interesting, but, you know, I don't know, it doesn't really get us too far. Okay, so what else can we do? Well, let's add some gas. Let's run the light through a cool gas. Okay, and when we do that, we get this. Right, here's my light source. There's a cool gas. Run it through, and I'm missing wavelengths, right? What's happening here is the gas over here is absorbing certain very specific and very consistent wavelengths. If I don't know what this gas is, I can identify it based on what I'm missing over here, right? So if there's cool gas out there in space with light running through it, for example, an atmosphere maybe, or something like that, right? Wait for some light to run through it and look at what you're missing, right? We can use these absorption or dark line spectra to identify the gas. And if it's more than one gas, you have more than one over here, but you get it sorted out, right? In the old days, you had you would have books of these spectra, right? And astronomers would just flip through the books and figure out what they were missing. Nowadays, they got fancy computers and can do all kinds of cool stuff. Okay, but fundamentally, if I don't know what this gas is, I can identify it based on what I'm missing over here. Now, I'm going to switch the slide, and what we're going to do is we're going to heat the gas. Same gas, but I'm going to heat it. Okay, now I want you to look at the pattern here. So 1 2 1 2 2 1, right? That's the pattern. Now I'm going to switch the slide, and I'm going to heat the gas. So when I heat the gas, that happens. Let me go back. We go from that to that. Right now, the gas is glowing. Right? It's emitting light, but only along certain wavelengths. And the wavelengths where before it was absorbing, now it's emitting. And once again, if there's a hot gas in space, we can use that to identify the gas, right? Now we have what's called an emission or bright line spectrum, right? And we can use, just like we use the dark line spectrum, we can use the bright line spectrum to identify the gas, right? So we have ways of identifying both hot and cool gases in space based on their spectra. You use an instrument called a spectrometer, which is basically a telescope with a prism in it. And it shows you, not just the thing you're looking at, but it shows you the light that it is putting off. And you can use that for all kinds of really cool things. And once again, this works because light is a wave. Okay. Another thing that works because light is a wave is the Doppler effect. The Doppler effect is a shift in a wavelength because something is moving. Okay, and you have all experienced the Doppler effect with respect to sound, right? You're standing along the road and someone goes past you just blowing their horn constantly, right? As they pass you, the pitch of that horn is going to change. Okay, you've all heard this. Now, I'm going to put a video up with this lecture from YouTube showing this happening as a car goes by. So if you're not sure what I'm talking about, I'm going to stop the recording right now and write this down. You stop the recording right now and go watch that video. Okay, wasn't that cool? Okay, so what's happening? Why is that pitch changing as that car goes by blowing its horn? Well, it's changing because the wavelength that you perceive as you're standing there changes as the car goes by. So here's an animation showing why this happens, right? So I've got a source of waves here, emitting waves. I've got an observer of waves here. They could be sound waves, they could be light waves. It doesn't actually matter what kind of waves they are. They can be water waves. It doesn't matter what kind of waves they are. We can just hear it with sound. Okay, and so yeah, so you got a source of waves here, you got an observer of waves here. The source is emitting waves at this wavelength. As long as nothing is moving, the observer will detect the same wavelength. Okay, now let me speed this up a little bit because it works better if you do that. And now what I'm going to do is I'm going to move the wave source, right? So when I do that, you can see how the waves in front of it bunch up. And so now you're going to hear one thing, and then right when it goes past you, that wavelength, or in the case of sound, that frequency changes, right? As it passes you, you go from hearing this to hearing this, right? And that point right there is when your perceived wavelength gets longer, okay? If it's sound, the pitch drops, okay? If it's light, it is going to quote unquote look, I'm putting little air quotes around look, redder, okay? And so what the Doppler effect is, it is when there is a shift in apparent wavelength between something moving toward you, when the wavelength will be shorter, and something moving away from you, where the wavelength will be longer. You can hear it in sound. You cannot see it with light, okay? The speed of sound is about 760 miles an hour at sea level, normal pressures, normal temperatures, etc. A car, even if it's only moving 10 or 20 miles an hour, is still moving a reasonable fraction of the speed of sound. Okay, the speed of light is 186,000 miles per second. There is nothing around you that is moving fast enough for you to see a blue Doppler shift or a red Doppler shift. Okay, we call them Doppler shifts because they will detect as redder if it's moving away from you. It will detect as bluer if it's moving toward you. Okay, but that's not something that you literally see. Okay, things are red and blue and everything in between for all kinds of reasons. So don't assume that everything that's moving toward you is going to look blue and everything moving away from you is going to look red. It's not, okay? You need very, very fancy instruments to see this, okay? But what does it, what does it look like? And I'm trying to switch my slide, and it's not wanting to switch, so let's go here, and let's go here, right? And so you can see here's a dark line spectrum, and there it is unshifted. Now, if the thing making this light is moving away from us, these lines are going to be shifted toward the red end of the spectrum. Now, this is a huge Doppler shift. Okay, most of them are tiny and you need fancy instruments to detect them, but nevertheless, there it is. If the thing is moving toward us, it will be blue shifted, right? And so this gives us a really handy thing. This gives us a really handy way to tell if an object in space is moving toward us or away from us, which is obviously a very, very good thing to know. But there's another application of this that's really fascinating. So when the Hubble Space Telescope first launched, they pointed it at an empty part of the sky. This is what the Hubble was built for, by the way. The Hubble was built to study other galaxies. I know that we really like looking at pictures of the planets and all these other interesting things taken by the Hubble. But where it really shines, what it was really truly built for, as I said, is to study galaxies. And so what they did was they pointed it at a very empty part of the sky. And they opened the shutter, like I think for literally like a week, like 7 days. They just opened the shutter and said, let's let some light bleed on here and see what we get. When you look at it with the naked eye, you don't really see anything. Let's see if there's really nothing there. And so they did that. At the end of the week, they shut the shutter and they said, send us the picture. Hubble sent back the picture, and it looks like that. So here's the thing. Every point of light in that picture is another galaxy. There is not a star in this picture. They are all galaxies, every one of them. Now, some of them are obviously so. You see that one there is kind of obviously, an accumulation of billions of stars like our Milky Way galaxy. There's another accumulation of billion. They're all that. But some there, that one really looks like it, right? That one right above my pointer there, really does, right? But they're all galaxies. These look that little thing, that's a galaxy, right? There's not a star in this picture. These are all galaxies. Okay, now here's the thing. Okay, ignore what color they look. Things look colors for all kinds of reasons, right? Just because someone is wearing a blue shirt does not mean that they are, moving toward you or something like that. If someone is wearing a red shirt, that doesn't mean that they're moving away from you. So ignore what color they are. When you look at the spectra from them, they're all redshifted. Every single galaxy that we have ever seen, except for one, and I'll show you that one in a minute, is redshifted. They're all moving away from us. Now, we're not in the middle. We're part of this, right? We're part of a large cosmic explosion or expansion of the universe, right? We're all moving away from everyone else, right? All our galaxy is moving away from all these other galaxies, except for one, the Andromeda Galaxy. So, like, if we're right here, the Andromeda Galaxy is like right there, right? It's the closest one to us. In fact, if it was brighter, that's what it would look like in the night sky. You can't see it because it's so dim, but that's how big it would look if it was brighter, several times the diameter of the moon. And our gravity and its gravity are grabbing a hold of each other, and we are being pulled toward each other. And so, so this is where we get the idea that the universe is expanding, right? That the part of the universe that has mass and matter in it is expanding outward. Now, here's the interesting thing, though, right? If we say, okay, everything's redshifted, so everything is moving away from everything else. If I run this backward, that means everything is moving toward everything else, and it's going to come down to a point about 14 billion years ago, right? When all of the mass was in the same quote-unquote place at the same quote-unquote time. I'm putting little verbal air quotes around space and time because space and time do not work the way you think they do when all the mass in the universe is at the same place. It just doesn't work that way. But that's going to create, a singularity, which you can kind of think of as a massive nuclear explosion, right? That is going to, make atoms out of subatomic particles, and suddenly, boom, everything starts, moving outward in this huge explosion that we have come to call the Big Bang, which is a horrible word for a very, very complicated idea. But the underpinnings of it are pretty simple. All the galaxies we see, except for Andromeda, are redshifted. They're all moving away from each other. And so if you just run that backward, everything is going to end up in the same place at the same time. And now, at that point, you need someone like Stephen Hawking to figure out the implications of that. But getting there is fundamentally not that difficult. Okay, so light is a wave, right? Light refracts because it's a wave, making those spectra, making rainbows and stuff like that. Light, it does the Doppler effect, right? The wavelength will seem to shift if the emitter is moving toward you. The wavelength seems shorter. If the wavelength is moving away from you, the wavelength seems longer, right? With respect to light, we call that a blue Doppler shift or a red Doppler shift, right? They don't look blue and red. I cannot emphasize that enough, okay? But they will detect out as being shifted toward the blue or red end of the spectrum. Here's the fun part, though. Light's also a particle. Light's also a thing like a rock or something like that, right? A discrete thing that can move or does move from one place to another. And Albert Einstein figured this out in the 1920s. he figured out that light is a particle. And he did it using something called the photoelectric effect. The photoelectric effect was something that physicists knew about at the time, but didn't really understand. And so let's take a look at how it works. So the experimental apparatus is really pretty simple. You have a metal plate here that is negatively charged. I have a metal plate here that is positively charged. I run a wire in between them, okay? Run the wire through a voltage meter so that you can tell if there's any current running through it. Put the whole thing in a vacuum just to be safe, and there you got it. It's not hard to do. Okay, then let's play with it a little bit, because here's the trick. You don't have a electrical circuit here, right? There's nothing here. Right, electricity doesn't flow across thin air like that. Okay, well, sometimes it does. That's called lightning, but that's the potential here is not great enough for that. Okay, but so no, right? So no circuit, no electricity. Okay, now let's do some stuff. Let's shine some red light on that thing. If I shine red light on that negative plate, nothing happens. Which, okay, what did you expect to happen? Right? Nothing happens, okay? But here's where it gets interesting. If I shine blue or ultraviolet light on that plate, I get electricity. Right? That voltage meter ticks. There's power running through that line now from shining light on it, right? This is how you build a solar panel, by the way. If you want to build a solar panel, light as a wave isn't going to help you. You need light as a particle, and here's why. Okay, so physicists knew about this, but they didn't know why. So Einstein says, okay, let's check this out. Look, what if we magnify that plate like a bazillion times, okay? Well, if we do that, it looks like this, right? That plate is made out of atoms, okay? And those atoms are surrounded by a cloud of electrons, right? You can't really draw it. It's not like 1, 2, 3. No. Electrons are very small. They're moving very near the speed of light. Even one of them is a cloud. Okay, so this is a cloud of electrons. Everything that exists, the outside of it, is a cloud of electrons. Okay, and so Einstein realized that what was happening here was the light was hitting electrons. Right, that's what was getting hit here were electrons. And he also realized that if light was behaving like a particle that he called a photon, that's a real thing, not just a torpedo in Star Trek, okay, that those particles of light would literally hit that cloud of electrons and knock some of them loose. Right, and Einstein realized this. He said, look, if light is behaving now like a particle, it's smacking that cloud of electrons, knocking some of them loose. Now let's go back over here, right? And so we've got loose electrons floating around here. Now electrons are negatively charged. That plate is negatively charged, right? So, and that plate's positively charged. So they're going to actually get pushed away from that negative plate and toward that positive plate, right? And so now we're moving electrons. Moving electrons is oddly enough called electricity, right? And so, sorry, I'm getting emails. Moving electrons is oddly enough called electricity. Okay, and so this is how you make a solar panel. Now you only use one, and it's fancier, right? But this is the fundamental thing that allows you to make a solar panel. That light is behaving like a particle, and when it hits that metal, it displaces electrons, and displacing electrons is fundamentally electricity, right? And so they looked at Einstein and said, that's pretty cool. You're pretty smart. If you can do that, you ought to be able to independently derive some things and do some fancy things. And he was. And so, so in 1922, they said, hey, come and get your Nobel Prize. So this is what Einstein won the Nobel Prize for, was this explanation of the photoelectric effect. It was good, it was basic, it was, in the end, very clear what was going on, but it took someone of Einstein's caliber to figure it out. He didn't win the Nobel Prize for relativity. No one was really sure about relativity, right? Everyone's like, really? You say that, okay. Okay, if you say so, but maybe not. But this was very clear and actually really very good work. There's another thing though that indicates that light is a particle, and that is comet tails. Right, here's a comet tail. There's a picture of a comet. Right, really pretty. I believe that one is called McNaught. So there's that tail strung out through the night sky. Really, really pretty. Right, here's another one. I don't know its name. Just random comet out there in space. Okay. So if I was to ask you though, what direction is that comet moving? Okay, you would say, and I would say too, that it's moving this way. Right, it's ing to the lower left here. It's moving toward my little laser pointer thinger there. Okay, but it's not. Okay, actually, well, it might be. The correct answer to the question, what direction is the comet in this picture moving, is you can't tell from this picture. Okay, comet tails don't string out behind them. Comet tails string out away from the sun. And so as that comet goes around the sun, that tail will always be away from the sun because light is behaving like a particle. It is smacking against that comet and it is physically knocking gas and dust and all kinds of things off of that comet, but it's going to knock it off the side away from the sun, not the side behind its direction of movement, right? We're so used to thinking about things moving like in an atmosphere or something like that, that we just kind of instinctively look at this and go, yeah, it's moving that way. Yeah, it's in space. We don't know what way it's moving. Now, what I can tell you is the sun is down here somewhere. Now that comet could be moving directly this way. It could be moving directly into that tail. We just don't know. Comet tails point away from the sun because light and all the radiation coming off of the sun is behaving like a particle. Okay, now, so light as a wave and a particle. There's two things for each. Okay, first of all, a wave. Light refracts because it's a wave, right? It will bend as it goes from one thing to another. Okay, and then light does the Doppler effect because it's a wave, right? The wavelength will shift as the emitter is moving either toward you or away from you, right? You can hear it with sound. You can detect it with light, but it takes a fancy instrument, right? And this is what leads us to the Big Bang and the expanding universe and all this other stuff, right? Particle, two things for that too, right? Photoelectric effect, right? If you're going to build a solar panel, light needs to be a particle, okay? You make electricity from light because it is a particle. And then comet tails, right? Comet tails always string out away from the sun, right? All of that radiation coming off of the sun is smacking against that comet and knocking it off of the backside. Okay, all right, that's light. Next time we will pick up with telescopes, and we'll talk about telescopes and we'll talk about the sun. Okay, until then, y'all take care and get with me if you need me. Okay, bye bye.